Hi there! In the last video of the Theremin, we examined the low-pass filter, which is part of the volume control unit. Today, we will keep working on the volume control unit, but we will concentrate on the peak detector, which is the element that converts the sine wave signal coming from the low-pass filter into a DC voltage that has the same amplitude as the peak of the sine wave. Before diving into the details, please take a moment to subscribe to this channel and click on the bell icon to receive notifications when new videos become available. The subscription helps keeping the channel alive, so it can serve you better. And now, let's begin! Here is the schematic of the peak detector. The input signal that comes at the anode of diode D1 is a sine wave which amplitude is modulated by the hand of the player moving in front of the volume antenna. And here is a picture reflecting this signal. Here I assumed that the hand of the player moves back and forth from the antenna, thus causing the ondulation on the sine wave. This ondulation will help describe what is about to come. Since the diode only allows the current to pass in one direction and not the other, it will let only pass the positive crests of the input wave, so after the diode the signal will have this aspect. However, at the diode cathode we have a capacitor that has the other lead connected to ground. This capacitor will charge at the max amplitude of the positive part of the sine wave coming from the diode, and will keep that value, since there is nothing that can discharge it. As a result, the signal at the input of pin 3 of the op-amp will be a perfect DC voltage. But since we really want a voltage that follows the peaks of the wave, we add the resistor R7 in parallel to the capacitor. This resistor will slowly discharge the capacitor during the descending sides of the sine wave. The RC timing is calculated in such a way that the capacitor will be able to discharge in about 0.2 seconds. Since this time is much longer than the period of the sine wave, the capacitor will only be able to discharge a little bit. In particular, it will only be able to discharge and recharge following the slow variation in the sine wave amplitude caused by the change of the frequency through the low-pass filter. So at the end, the signal at pin 3 of the op-amp will really be like this. Note that this picture is an exaggeration, because the frequency of the original sine wave is much higher than the changes in amplitude caused by the hand in front of the antenna. So, in reality, that sawtooth that you see in the picture will be much smoother. We will soon see that in the lab. So, the effect of the diode, the capacitor and the resistor is just to convert the modulated sine wave into a DC signal that can change its amplitude in time intervals longer than those 0.2 seconds calculated for R7 and C12. At this point, the signal enters the non-inverting input of the op-amp, which is configured as a voltage follower. So, we will find exactly the same signal at the output of the op-amp. The only difference is that we will be able to draw some current from the op-amp output, current that we could not draw at the lead of C12, or we would have altered the functionality of the RC group. This signal at the output of the op-amp, after some adjustments in amplitude, will be used to control the last stage of the volume control unit, but this is a subject for another video. Instead, let's now move to the lab to see how this peak detector circuit works in practice. Let's now take a look at how I built the peak detector on the breadboard. We can see from the circuit that the input signal enters on the anode of diode D1. On the breadboard I am using as input the signal coming from the low-pass filter, which, as you can see, comes into the anode of the diode. The signal at the cathode of the diode is filtered through capacitor C12 and resistor R7. And here they are on the breadboard. From there, the signal goes to the non-inverting input of the operation amplifier, pin number 3, which is right here on the circuit. The inverting input of the op-amp, instead, is connected to the output of the op-amp itself, thus creating the voltage follower. You can see the blue wire that connects pin 3 and 6, which are the inverting input and the output of respectively. The output of the peak detector is also taken directly from pin 6 of the op-amp, where we have connected the oscilloscope using the probe labeled in blue, which of course goes to the input marked in blue of the oscilloscope, which is the channel 2 input. The other channel of the oscilloscope, marked in yellow, is connected to the output of the function generator, so we can see the signal that goes into the input of the low-pass filter. And here is the cable that brings the input signal from the function generator to the input of the low-pass filter, which we analyzed in the previous Theremin video. So, basically, we have a signal that enters the low-pass filter, which will output a similar signal but with an amplitude that depends on the frequency of the signal itself. The output of the low-pass filter enters the peak detector, where it is rectified and filtered by diode V.1, capacitor C12 and resistor R7. And finally, the output of the peak detector goes to channel 2 of the oscilloscope, the blue one. If I now change the frequency of the signal on the function generator, you can see it increasing on the oscilloscope yellow trace, and you can also see that the voltage of the peak detector output drops. Vice versa, if I decrease the frequency, you can see how the voltage of the peak detector output increases. So, by changing the frequency of the signal entering the low-pass filter, we can change the DC voltage level at the output of the peak detector. Let me show you now the effect of the capacitor in this circuit on the signal. I am temporarily pulling the capacitor out of the circuit. Look what happens to the output of the peak detector. See, the signal is still all positive. This arrow indicates the zero value of the voltage. Without the capacitor, it is not anymore a constant value. It is instead a signal that has the same frequency as the input wave. Let me now put back the capacitor. You see, as soon as I do that, the signal becomes again a constant voltage. So again, if I decrease the frequency of the input signal, the DC voltage of the output becomes higher, and if I increase the frequency of the input signal, the DC voltage of the output of the peak detector becomes smaller. In this video we went through the description of the peak detector used in the volume control unit of the Theremin V.2. We saw how the amplitude of the output signal is a DC voltage that resembles the peak value of the input sine wave. When I changed the frequency of the sine wave, I changed its amplitude because it passed through the low-pass filter. The change in amplitude of the sine wave was translated in a change in amplitude of the DC voltage at the output of the peak detector. In the next video of the Theremin, we will see how the output of the peak detector will be manipulated to change its amplitude in the range required by the voltage controlled attenuator, which is the last stage of the volume control unit. This manipulation will be done by the voltage range adjuster. Thank you for watching this video, and don't forget to give it a thumb up, which will greatly help improve its visibility so others can enjoy it too. Also, if you have not subscribed to the channel yet, please do so now to help making more and better videos. Talking about help, a small monetary contribution can help too. There are a couple of options you can choose from: Patreon and PayPal, both listed in the video description below. See you in the next video, and as usual, happy experiments!